In this video, we're going to look into integration by partial fractions through this example. We try to integrate this function 10 over x minus 1 times x squared plus 9. And the partial fractions method is used on rational function only. And the rational function is defined as the quotient between two polynomials. And this is the first thing we do. We got to check, yes, I do have a proper rational function. Proper means the degree on top is less than the degree at the bottom. The degree on top is a constant as degree 0. At the bottom, once you find the expansion, we're going to see the degree is going to be 3. So we proceed to write this as the sum of two partial fractions with each factor as the denominator. And as a proper rational function, this must be a over x minus 1, bx plus c as the numerator for x squared plus 9. And notice x squared plus 9 is what we call irreducible quadratic. Irreducible quadratic means I cannot factor over real numbers. And next step, we're going to combine two partial fractions so that I have a times x squared plus 9 plus x minus 1 times bx plus c. And we combine this as ax squared plus 9a plus bx squared minus bx plus cx minus c over x minus 1 times x squared plus 9. Now we're going to combine like terms, which we have as a plus b x squared plus negative b plus c of x and plus 9a minus c over x minus 1 times x squared plus 9. And now we're going to recall, where was this coming from? This function actually came from here. It means that these two functions are equal. If they have same denominator, they must have same numerator. When we say the same numerator, we mean they must have the same corresponding coefficients, got to be the same. So we set up equations based on the corresponding coefficients. The coefficients for x squared in this function, there's no x squared, means the coefficient is going to be 0. So the coefficient a plus b must be 0. And negative b plus c must be 0 as well. 9a minus c is going to be 10. And okay, now we got to save some space. We need some space. I'm going to move this up a little bit. I'm going to move this up here, say. When we observe these three equations, we were taught solving system equations. When you have three unknowns, you take two different pairs, eliminate same unknown, reduce to system of two, and so on and so forth. So when we look at the top two equations, we notice, look, if I add these two equations, I get rid of b by elimination. But if I add the bottom two equations, I will get rid of c. Therefore, nobody's going to stop you from adding all three equations at once. This way, I get rid of b and c together. I just have 10a equals 10 left, which give me a as 1. Therefore, from the first equation, I get to know b is going to be negative 1. C is going to be 1. From the second equation, indicate b and c are the same. From these results, I get to know now this function or this integrand actually can be written a little differently in this form. Say 10 over x minus 1 x squared plus 9 dx can be written as a over as 1 over x minus 1. So that's from here, a over x minus 1. And the plus negative x minus 1 over x squared plus 9 dx. I integrate this function. And we're going to write it here. Find the antiderivative for the first term should not be a problem. We make a simple substitution. and the antiderivative is going to be natural log of absolute value of x minus 1. And then we look into the next two. The next two, I mean 2, is because how do we integrate this? We're going to split this into two terms. So we're going to integrate negative x over x squared plus 9. And I'm going to take a negative sign out. And 1 over x squared plus 9. The antiderivative for each, I'm going to write out the final solution. Copy the first. The antiderivative for this, we can use a substitution, let the denominator be u. So the antiderivative is going to be 1/2 natural log of x squared plus 9. And the last one, I hope we can recognize the form of the formula 1 over x squared plus a squared. Therefore, the antiderivative is going to be 1 over a, that's 1 over 3, inverse tangent of x over 3. And that will be our final solution.